Good morning. Hope everybody's doing all right today. So we are going to pick up where we left off in section 2.2 yesterday and finish up some of these limit definitions of derivatives. And then we'll get into 2.3, which is actually the shortcuts. And so then you should be able to do all the homework for 2.1 to 2.3. Remember, I did move that due date to tomorrow night at midnight. So hopefully we'll finish up enough of 2.3 today that you should be able to get that homework done. And then I moved the next homework assignment to Monday of next week. We'll see how far we get by Thursday. And then if I need to adjust that again, I will. But you've at least got the weekend on the next homework assignment. Okay. I think that's all I've got. Any questions, comments, concerns before we get started this morning? All right, so some other notations that we can use for our derivatives here. So remember the ones we've looked at so far, f prime of x is the main one that we're probably going to use, right? So anytime you have a function, you're looking for the derivative, we're going to call that f prime of x. Some other notations though, we could use y prime. So instead of writing the f prime of x, if you just have a y equals equation, you're finding a derivative, a lot of times we'll use the y prime notation. Dy dx is another notation that we're going to use for derivatives a lot. Those first three are the main ones, okay? So those are the ones we're going to see most often. But if you ever happen to see any of these others, they're all equivalent to each other. So df dx is the same thing, so we're finding the derivative of the function with respect to x. Same thing with d dx f of x. It's very similar to the previous one. You could also use just a capital D to represent derivative of a function, or you could use a D with a subscript of x to represent a derivative. Okay, but again, the f prime of x, y prime, and dy dx, those are the three most common ones. Those are the ones we're going to use in our class. Okay. But again, whenever you're calculating these derivatives, we're using that limit definition where the delta x, or the change in our x values, is approaching 0, and that's what we let the h value be equal to, and then we find the slope, right? So that's the change in y over the change in x. So no matter which type of derivative you're looking for, it's always that same thing. Okay, so we're trying to approximate the slope at a given point. That is what the slope of our tangent line is what a derivative is going to represent in any case. Okay, right now. A function f is what we call differentiable at a if f prime of a exists. Okay, so basically, if you can take a derivative at that specific point, then we call the function differentiable at that point. If it's differentiable on an open interval from a to b, or from a to infinity, negative infinity a, so on, okay, if it's differentiable at every number in that interval, okay, so we call it differentiable on an open interval if it's differentiable everywhere in that interval. A lot of the functions we look at are actually going to be differentiable across all real numbers, right? Polynomial functions would be an example of that. You can find the derivative at any point on a polynomial function. Okay, but there will be some where we have restrictions on the domain. Obviously, you can't find a derivative if the value doesn't exist at all, right? There's also going to be some other places where we can't find derivatives. Okay, but we'll look at that as we go. All right, so here, example 5, we want to know where is this function f of x equals absolute value of x differentiable? And so we're asking ourselves, where can we actually calculate a derivative for that function? So there's a couple of different ways we can think about this. First off, what does the graph of this function look like? It's a V. Good, right? So remember, we've looked at the absolute value function before. If we sketch the graph, we know it's a V graph, has a point here at the origin. It's going to go up and to the right that way, up and to the left that way. Okay. Now, remember, a derivative here is just going to represent the slope of a tangent line. So let's think about the left-hand side of this graph. So if I'm looking from negative infinity up to 0, right, what would the slopes of my tangent lines be for everything on the left-hand side of the y-axis? And I'll give you a hint. With a linear function, the slope of the line is the slope of your tangent lines. Okay, so even though I understand a tangent line would go through every point along that line, if you have a linear function, because that slope is consistent, the slope from the left and the right is going to be the same. So what would the slope be everywhere on the left-hand side of this graph? Okay, it's going to be negative, right? And specifically, it's going to be negative what? What's the specific value going to be on the left? -1, right? So if you remember, right, if you think about this, this is going over 1, up 1 from the origin every time. Okay, and so we have a slope of -1 on the left-hand side. So what we could say in this case is that on the interval here from -infinity to 0, the limit as h approaches 0 of f of x plus h minus f of x over h, okay, which just represents our derivative now, right, is going to be equal to -1, because that's going to be the slope at every single point from -infinity all the way to 0. Now, what about the right-hand side of this graph? What is that going to be? It's going to be +1, right? Because in this case, we're going to the right 1 and up 1. And so everywhere on that side of the graph, from 0 all the way to infinity, our limit as h approaches 0, f of x plus h minus f of x all over h is going to be equal to +1. What that tells us then is that our derivative exists everywhere from -infinity up to 0, and it's just equal to -1. Our derivative also exists everywhere from 0 to infinity, and it's equal to +1. Now, for the derivative to exist at any point, it has to be the same from the left and the right. Okay, so that limit needs to be the same from the left and the right. At 0, what is the limit of our slope from the left and from the right? Are they approaching the same value? They're not, right? Because on the left-hand side, we've already said it's going to be -1 as our slope. On the right-hand side, the slope's going to be +1, and so those values are not approaching the same thing. So we would have to say in this case that our limit, I'm just going to say as x approaches 0 from the left, and it's really of this slope formula, right, is not equal to the limit as x approaches 0 from the right. Therefore, it is not differentiable at x equals 0. And that's the only place on this graph where that happens, right? Because every point on the left from -infinity to 0, that slope is going to be consistent. So my limit for my slope from the left and the right is always going to be the same. And on the right-hand side, same thing. My limits from the left and the right for my slope always going to be equal to 1. And so I know that that is differentiable on that side. The only place where that doesn't happen is where those two lines meet now at 0, 0. And so that limit of my slopes is not the same from the left and the right, and therefore it is not differentiable at 0 anymore. Any questions on that? Okay, now this is one of the visual things we're going to want to look for whether a function is differentiable or not. Anytime you have a sharp point like that, okay, so in this case, those two lines come together, they form a sharp point. It's not a smooth curve here, and that's going to be a point where it is not differentiable, because in all of those cases, your slopes from the left and the right are not going to be the same. So anytime you have a sharp point, just know at that point, it's not going to be differentiable. Okay, so here's some places where we cannot find a derivative, okay? So first off, if f is differentiable, then it has to be continuous, okay? So just keep that in mind. So if there's any discontinuity there, then we know the slopes from the left and the right can't be the same, therefore it's not differentiable there. Okay, but some places where we don't have derivatives, this sharp point, right, like we said before, okay, it's not differentiable at A in that case because we have what we call a corner there. Okay. If you have a discontinuity, so here we have a point up here and a point down here at A, right? We have this jump discontinuity in our graph. Therefore, it is not going to be differentiable at A for that second graph. And the third possibility is that we actually end up with a vertical tangent. And remember, the slope of a vertical line is undefined. And so anytime your graph gets steep enough, okay, that you actually have a vertical tangent there, then we would say that is not differentiable at that point either. So those are the three examples of where you would have a function that is not differentiable at a point. Sharp points, discontinuities. All right, now we can also take higher order derivatives of our function. So far, everything we've looked at has just been what we call a first derivative. We've taken the derivative one time. Okay, if f is differentiable, then its derivative f prime is also a function, so f prime might also have a derivative of its own. And we would call that f double prime. Okay, and so we're going to denote that the derivative of the derivative, we're just going to use two prime marks here and say that's f double prime. So that just represents the derivative of the derivative. So we call that a second derivative, and then we can take a third derivative, a fourth derivative, okay, as many times as we want to until we get something where it's not defined anymore, right? Because there are times where you won't be able to take, a third or fourth derivative because the function that you get for one of those derivatives doesn't have a derivative at all. And down at the bottom, you'll see there's just another notation for that. Again, the main one we're going to use is like f double prime of x, y double prime. But you could also see this second derivative notation down here. Not as common, okay, but if you see that, that just means second derivative. All right, so let's take a look at this one. So we want to find the second derivative and then think about what that second derivative actually means. Well, if you remember, we looked at this function earlier. We already found the first derivative, right? So what was the first derivative of x cubed minus x? This was back in example 2. Good. 3x squared minus 1 was our first derivative. All right, so now that derivative is itself a function. So we can actually take the derivative of that derivative now, and we want to find the second derivative. Well, we're going to use our limit definition again here to find that derivative. But when we do our limit definition, we just want to make sure that we're using the f prime of x as the function that we're looking for. So we're going to find f prime of x plus h minus f prime of x all over h. Okay, so same formula, we just have to make sure we're substituting into the first derivative this time if we're looking for the second derivative. All right, so if we do that, what is f prime of x plus h going to look like? Good, right? So we take the 3, we're substituting the x plus h in for the x here, which means we have to square it, and then we're going to subtract 1. And then down here, we're subtracting f prime of x, which is just 3x squared minus 1. And we're putting all of that over h. All right, now we're going to simplify this. So remember, x plus h squared, that should give us x squared plus 2xh plus h squared. Bring down your minus 1. And now I'm going to distribute this minus and get a minus 3x squared and a plus 1 all over h. All right, now this time we do need to distribute at this point, so I'm going to distribute my 3, and then we can combine like terms. We have 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1 all over h. Okay, now this time, if we combine like terms in the numerator, what's going to be left? Good. So just the 6xh and the 3h squared, right? Because our 3x squared minus 3x squared cancels, our minus 1 and plus 1 cancels. So now we're looking for the limit. H approaches 0 of 6xh plus 3h squared all over h. And at that point, we can do what? Good. Factor out the h. Limit as h approaches 0. H times, that's going to be 6x plus 3h all over h. Now we can cancel out the h factor, numerator, denominator, and we should be able to calculate this limit now. So what would our limit as h approaches 0 of 6x plus 3h give us? Good, right? Because the 3h just becomes a 0, and so this is just, 6x plus 3 times 0, or just 6x. So in this case, f double prime of x is 6x. Okay. Now, what does the second derivative represent? So think about what we know about derivatives, right? We know the first derivative is the slopes of the tangent lines of the original function at any given point. So what do you think the second derivative represents now? Okay, so when we get to looking at velocity, position, and all that, right? That you're correct, right? Acceleration is where we're headed in terms of real-world problems, right? Actually, practical applications. Let's just think generally, right? If we just have functions that don't represent position, velocity, what would the second derivative represent now? Okay, good. It's the slopes of the tangent lines of the derivative function, right? So if we think about it this way, we know that the original function, when we find its derivative, we're finding rates of change, right? So those are the slopes of the tangent lines, the rates of change of that original function. Now we're looking at the rates of change of that rate of change function, okay? So we're finding the rate of change of a rate of change of an original function. That's what this is. Okay? But in general, it's the slopes of the tangent lines of that first derivative function, which itself represents rates of change. Yes, when we get to actually applications of this, okay, that's why it will represent acceleration, because the acceleration then is going to represent a rate of change of the velocity, right? So it's a rate of change of a rate of change. Any questions on this one? All right. Now, here we go. Velocity and acceleration. Okay, so v of t is equal to s prime of t. So remember, s of t is our position function. v of t is velocity. And now we're going to have an a of t function, which represents acceleration. Okay. So if we want to know the velocity of something, we can take the derivative, which is the rate of change of a position function. And we'll call that s prime or ds dt, because we're taking the derivative with respect to time now. Then the acceleration is going to be the first derivative of velocity, which would also be the second derivative of our position function. So if you're given a position function and you want to know the acceleration now, we need the rate of change of the rate of change. So we have to go all the way to the second derivative of position to get to acceleration. And again, these are just different notations that we can use for these. Okay, but just keep in mind, basically, we have our position function. If you take the first derivative, that gives you velocity. If you take the second derivative, that gives you acceleration. All right, now, like I said, we can take even higher order derivatives beyond 2, right? So we can take a third derivative. Again, the way we're going to do that is we're going to use 3 primes here. Let me actually, I've got a typo in that second line, so let me fix that real quick. There we go. All right, so basically, if we're finding the third derivative, we're just taking the derivative of the second derivative, right? Okay, so we can use 3 prime marks to represent that, okay, but it is just equal to the derivative of the second derivative. Now, if we want to go beyond third derivatives, then we're actually just going to use this notation down here. So like if I wanted a fourth derivative, I would call that the fourth derivative of y. Or if I wanted a fifth derivative, I would call it the fifth derivative of y, and so on. Okay, and that's just so we don't end up with all these tick marks and we're trying to count them up and it gets really confusing and blended together. So we just use parentheses, okay, so that way it doesn't look like an exponent. So that would mean the fourth derivative or fifth derivative. But anything up to a third derivative, we'll just use prime marks for that. All right, so now we're given that same function again. We want to find the third and the fourth derivatives of that function. Now remember, we just found the second derivative, so I'm going to go ahead and write that down. Remember, f double prime of x was 6x. So if we want to find the third derivative now, how are we going to do that? Good, right? So without doing any work at all, we know that 6x is a linear function. We know the slope of that function is 6 at all points on the line. So we know the derivative represents the slope of the tangent lines to that function. Therefore, this is just going to be 6. So without doing too much work, you just think if you have a linear function and you're finding a derivative of a linear function, it should just be the slope of that line, okay, because that's what the tangent lines are going to be, right? Again, where no matter what point I choose on that line, that's what the slope is, and that's how I know the third derivative is just going to be 6 here. Now, if you use your limit definition and canceled things out and simplified and everything, you'd get the same answer, right? But there's really no reason to do all that work in this case because we have a linear function that we're finding the derivative of. What about the fourth derivative? Good. Y equals 6, right? The third derivative here is a horizontal line. Horizontal lines have slopes of 0. And so this right here, the fourth derivative, since it just represents the slopes of our tangent lines to that other function, is just going to be 0. And again, if you want to see the graphs of these, just to make it a little more clear, our second derivative was 6x has a y-intercept of 0. Rise over run, we're going to go up 6 and over 1. So we have this linear function that looks like this for our second derivative, and the slope of that is always 6. That's how we get the third derivative. Then if we were to sketch the graph of the third derivative, f triple prime, now we just have a horizontal line at 6. So we have a constant function there, and that slope is always going to be 0. Therefore, the fourth derivative would be 0 in this case. Any questions on that one? And again, if you had used your limit definition with the f triple prime being equal to 6, and you simplify all that, you'll see that it actually works out to just give you 0 anyway. Okay, so you can actually use the limit definition. We just don't really need to in this case whenever you have a linear function. All right. So that's everything from 2.2. So now we're going to go into 2.3. And like I said, this is where we're going to learn some of our shortcuts to find these derivatives. All right, so these are our differentiation formulas. And so we're going to look at a bunch of different ways that we can calculate derivatives where we don't have to use the limit definition anymore. And we're going to start out with some basic ones here. So if you have a constant function, okay, we're going to call that C, the derivative of a constant is 0. And we just saw that on the last example, right? When we had a constant function at 6, the slope was always 0. Therefore, the derivative of any constant function always going to be 0. And then our next one here, we have the derivative of x. X would be a linear function. The slope of that linear function would be 1. And so if the slope is always 1 along that line, the derivative is just going to be equal to 1 now. And again, this ddx notation is just another way to say we're taking the derivative of whatever we have there in parentheses. Oh, and let me make sure this is clear too. Whatever you put down here at the bottom, this tells you what you're taking your derivative with respect to. This is a derivative with respect to x. If you put a dt down there, then you're taking the derivative with respect to t. Okay, so it kind of depends on what variable you're working with in your function as to what you put down there to tell what type of derivative you're taking. Any questions on those two derivatives? All right. Now, if n is a positive integer, then when we find the derivative ddx of x to the n power, what we're doing is we're taking the n and we're bringing it out front, and then we're subtracting 1 from the exponent. So let's look at an example of this. If we want to take the derivative of x to the 5th power, if we follow that formula here, what would the derivative of x to the 5th power look like? Good, right? So we're going to bring the 5 to the front. We're going to keep the x, And then we're going to subtract 1 from the exponent. So 5 minus 1 should give us 5x to the 4th power now. And that's what we call our power rule. So whenever you have something of that form, x to some power, and you're looking for the derivative, all we have to do is bring the exponent out front, subtract 1 from the exponent, and we've got our derivative. Any questions there? All right, let's try these. So we've got f of x equals x to the 6th. We want to find f prime of x. So what should f prime of x be for that function? So if we just apply the power rule that we just looked at, what would the derivative of x to the 6th power give us? Good, right? So we bring the 6 out front, keep the x, subtract 1 from the exponent. That's going to give us 6x to the 5th power. That's it. That's all you got to do. Any questions on that one? All right, y prime. Okay, same thing. We're looking for the first derivative here of x to the 1,000th power. Good. So we bring the exponent out front. That's 1,000. Keep the x, subtract 1 from 1,000. That's going to give us 999. And we're done. Any questions there? All right, so the next one now, dy dt, and again, we're taking the derivative with respect to t because our function has a t this time, should give us, good, 4t to the 3rd power. All right, and then the last one here, we're taking the derivative now with respect to r because that's what's in our function. So what's our derivative going to be this time? Perfect, 3r squared. That's it. Any questions on using the power rule for any of these now? All right. Now, if we have a constant in front of our function, as long as f is differentiable, we're allowed to bring the constant out front. Okay, so in this case, we've got the derivative of c times f of x. We just bring the constant out front and then take the derivative of f of x like we normally would. Okay. All right, so I want to apply that to these, right? And then I'm going to show you that we could even shorthand it a little bit more than that. So if we look at this first one here, we're taking the derivative of 3x to the 4th power. What's the constant this time? 3, right? So I'm going to bring the 3 out front, and then I'm just taking the derivative of x to the 4th power. Well, we know how to find the derivative of x to the 4th power now, so I'm just going to keep my 3 times, what's the derivative of x to the 4th? So be careful here. 4x to the 3rd, right? So remember, we bring the exponent out front, and then we subtract 1 from the exponent. Okay, so it's going to be 4x to the 3rd there. Now we can multiply these together, right? So I'm multiplying the constant that I brought out front times the 4x cubed. And so what's that going to give us overall? 12x to the third. Good. Okay. And that is our derivative, right? So that's our final answer there. Now, you don't have to do all of these steps every time, because in this case, all we're really doing is we're multiplying this 4 times this 3 right here. Okay, because 4 times 3 is 12. Subtract 1 from the exponent, you could go straight to 12x to the third there. So you don't actually have to show the step of bringing the 3 out front, then taking the derivative of x to the fourth, and then multiplying them back together. You just want to multiply 4 times 3 to get 12, subtract 1 from your exponent, that'll give you your answer. Any questions there? Okay. What about the derivative of negative x? So what type of function is negative x? It's linear, right? What's the slope of that line? Negative 1. What should the derivative of this be? If that was supposed to be the answer here, if you were answering the previous question. In this case, it is going to be negative 1, right? Because if we know it's a linear function, we know the slope of that line, we're just finding the slopes of the tangent lines. Well, at every point along that line, the slope's going to be the same, and so that should just be negative 1. Now, if you want to show the steps for this one, we have a coefficient of negative 1 that can be brought out front. We could bring out the negative 1, multiply by the derivative of x. We already said the derivative of x here should just be 1. So we have negative 1 times 1, but that's still just going to give us negative 1. So whichever way you want to think about it is fine. Okay, but in this case, if you just recognize it's a linear function, slope is negative 1, therefore the derivative should be negative 1. Any questions on that one now? All right. Now, if we have two functions, f and g, and both of them are differentiable, we're allowed to split up the derivative. Okay, so just like we could with our limit laws, we're allowed to split up derivatives the same way. So we're going to take the derivative of f of x, derivative of g of x, and then add those derivatives together. Again, I know I'm not spending a lot of time on these slides, but again, the slides are posted, right? So if you want to go back and see any of these formulas, you can. Right, now, the same thing with subtraction, right? We can split that up just like we did with our limits. We can do it with derivatives. So we're going to take the derivative of f, derivative of g, and then just subtract those derivatives now. All right, so now we want to find the derivative of this function. All right, so keep in mind we have our power rule that we can work with now, and we know we can split up addition and subtraction and find each of those derivatives individually. So if we just go down the line here and we find the derivative of each of these terms and just put them all back together using addition and subtraction, that should be our derivative. So let's start with the first term. What's the derivative of x to the 8th power going to give us? Okay, so I like the 8 at the what power? 7th, right? Okay, subtract 1 from the exponent, that should just give us a 7. Now we have a plus. Now we want to find the derivative of 12x to the fifth. So remember, you could bring out the 12, find the derivative of x to the fifth, and then multiply them back together. Or we could just multiply the 5 times the 12 and then subtract 1 from the exponent. So what should that give us as the derivative for that term? Good. 60x to the fourth power. Okay. Then we have minus. What about 4x to the fourth? It's going to be 16x to the third. Good. Plus, what about 10x cubed? It's going to be 30x squared minus, what's the derivative of 6? It's just going to be 6, right? So minus 6 in this case. And then what's the derivative of 5? 0, right? Because the derivative of a constant should always be 0. And so we can just ignore that term altogether when we're finding our derivative. And we're done. That's our derivative. Okay, so no other work to be done there, just using our power rule and the fact that we can split up the addition and subtraction. Now we found our derivative. Remember, if we didn't have this and you had to use your limit definition, you'd be substituting x plus h into all of those x's, expanding out, canceling out like terms, factoring out an h, canceling out the h, then substituting a 0 in there to find this derivative. Okay, and just, x plus h to the 8th power is not fun to calculate, right? Okay, so these shortcuts definitely save us a lot of time now. Any questions on that one? All right. Now we want to find the points on the curve y equals x to the fourth minus 6x squared plus 4, where the tangent line is horizontal. So I want you to read through that, think about what we're looking for, and then tell me what you think we might want to do first to help us find those points. So any thoughts on what we might want to do first here? Okay, good, right? We're definitely going to need to take the derivative because we know we're working with a tangent line, right? And remember, we know that the derivative represents the slopes of the tangent lines. And because we want this to be a horizontal tangent line, we know the slope of that tangent line needs to be 0 then. So if we can find the derivative, that's the slope of the tangent line, we can set that equal to 0, and that's going to help us to find those points where that would happen. Well, let's find our derivative then. What's the derivative going to be this time? Good, right? So just bring the 4 out front, drop the exponent by 1. That gives us 4x cubed for the first one. Then we can just multiply here. 2 times negative 6 is going to give us a minus 12x. And when we subtract 1, that just gives us x to the first power. And then just remember the derivative of any constant, the 4 down there is just going to be 0, so it goes away altogether. Any questions on that derivative? Okay, now that we have the derivative, and like Dean said, we're going to set that equal to 0 because we need our slope to be 0 now. So we're going to say 0 equals 4x cubed minus 12x. Now, how would we solve that? Okay, good. We have a common factor of 4x. Let's go ahead and factor that out. That would leave us with x squared. And then over here, we're just going to have a minus 3. All right. Now what can we do? Okay, so we don't quite have a difference of squares, right? Because 3 itself is not a perfect square, so we can't really factor that x squared minus 3 very easily. So what can we do instead? Yeah, just set each of our factors equal to 0 now. So I'm going to take the 4x, set it equal to 0, then take the x squared minus 3, and also set it equal to 0. So once you've got your factors, just set each factor equal to 0. Well, what are we going to get for this first one then if I solve for x? X equals 0. Good. And then what would we have to do to solve x squared minus 3 equals 0? Good. Add the 3, so x squared equals positive 3. And then we can do what? Take our square root. And so what are we going to get as our x values here? We get square root of 3, but don't forget it is a plus or minus. Right? So plus or minus square root of 3. Any questions up to that point? Okay, so we're almost done, okay, but it wanted us to find the points on that curve where the tangent line is horizontal. So far, we know the x values where it's going to happen. So what are we going to have to do now if we want the points? We need to plug those x values back into the original equation to find the corresponding y values. So we'll start with 0. So we've got y equals 0 to the 4th minus 6 times 0 squared plus 4. So that's going to give us y equals what? Y equals 4. Good. Then we can do the same thing with the positive square root of 3 and the negative square root of 3. So we'll have y equals, start with positive square root of 3 to the 4th minus 6 times square root of 3 squared plus 4. And what's square root of 3 to the 4th power going to give us? It's going to be 9. Good. Because when you square it, you get 3, and then when you square it again, that'll give us 9. We have minus 6 times, what's the square root of 3 squared? Just 3. Good. And we have our plus 4. So now if we work that out, 9 minus 18 plus 4, that should give us what? Negative 5. Good. All right, so we have y equals negative 5 there. Now, we do need to check the negative square root of 3. Okay, but if you notice here, I'm raising everything to even powers. So what's that going to give us if we work this out now? Same thing, right? Negative 5. All right, so now that we know the corresponding y values for each of those, okay, let's think about these points. So what's one of the points going to be this time? 0, 4 would be 1 point. Okay. Another point would be square root of 3, negative 5. Good. And then our final point is just going to be negative square root of 3 and negative 5. Good. So these are the points on that curve where we should have a horizontal tangent line. Any questions about any of the steps that we did there? Okay, now let's look at the graph, right? Because it's always nice to look there, kind of check yourself, make sure your answers make sense. So our original function this time was x to the fourth minus 6x squared plus 4. Zoom out here so we can see everything. All right, and if you notice here, right, the 3 points that we got, I'll actually plot them here. 0, 4 was one of those points. You can see that's the point right up here. We would have a horizontal tangent there because our curve changes direction at that point. If you look at negative square root 3, negative 5, that's the point right down here. Again, we have that change in direction, horizontal tangent at that point. And then our final point was positive square root of 3, negative 5. And that's the point on the other side, right over there. So don't be afraid to actually check yourself, right? Graph the original function, make sure the points that you got actually line up with changes in direction if you're looking for horizontal tangents, right? Because you should have, there's going to be a horizontal tangent there, and we know it has to change direction at that point. Any questions there now? All right. Example 5. So the equation of the motion of a particle is S equals 2t cubed minus 5t squared plus 3t plus 4. S is measured in centimeters, t is measured in seconds. And we want to find the acceleration as a function of time, and then we want to know the acceleration after 2 seconds. So I'm just going to fix this so that it's all on the same line. Hopefully I can do that. There we go. All right, so if we're looking for the acceleration as a function of time, what's the first thing we're going to have to do here? Okay, we need to find a derivative, right? Because this function, remember, s of t represents a position. Right? So if we find the derivative s prime, that's right. Okay, so the first derivative here is going to represent our velocity. So s prime should give us our velocity function. Well, what is that first derivative going to be this time? Good, right? So we have 6t squared minus 10t to the first power plus 3. Any questions about how we got the first derivative here? All right, so now if we're looking for acceleration, now we need to go to the second derivative. So we're looking for the second derivative of position, which is going to be the derivative of velocity, and that will give us our acceleration. So what is that second derivative going to be equal to? Perfect, 12t minus 10. Any questions on finding the acceleration function? All right. So then the question is, what's the acceleration after 2 seconds? So how are we going to find that? Just plug in 2. Good. So we know our acceleration function. We know our t value. We're just going to plug that in. So that's going to give us 12 times 2 minus 10, which would be what? Okay, good. So 12 times 2 is 24, minus 10 should give us 14. Now think about your units, right? Because we need to make sure we have units on these types of problems. What would the units for acceleration be measured in here? Okay, so centimeters represents position. Centimeters per second would represent velocity. So how would you represent acceleration now? So it's not just going to be seconds, because that would just be a time value, right? So we need an acceleration, which in this case represents some relationship between our position and our time. But it's not just centimeters per second, because that's our velocity. There it is, centimeters per second squared. Okay, so whenever you're dealing with acceleration, it's going to be your unit of distance over your unit of time squared. If you think about it, it's because we've taken that derivative with respect to time twice now, right? So when you take it once, you get velocity, centimeters per second. Then once you take the second derivative, we've taken another respect to time. So that's why we get second squared in the denominator. Any questions on that one? Again, just keep in mind this relationship between position, velocity, acceleration, because this is going to keep coming back over and over and over again throughout all the units that we do, basically. Okay. All right, let's take our break here, and then we'll do product rule when we come back. Okay, so 5 minutes. We'll get started back at 11:03. All right. Okay, so if we're looking at the product of two functions and we're trying to find the derivative, okay, we can't just find the derivative of each and multiply like we did with addition and subtraction. Okay, so we have this other formula now, and it looks a little crazy, right, with all the notation over there. And we'll show you a shortened, simplified way to write it. Okay, we're taking the original f of x function, multiplying it by the derivative of the g of x function, and then adding the g of x function times the derivative of the f of x function. In other words, shorthand, we're taking f times the derivative of g plus g times the derivative of f. Okay. So that's how I'm going to write it from here on out as we go. Okay, so it's f g prime plus g f prime. That is our product rule. Anytime you have the product of two functions and you're finding the derivative, that's the formula we have to use. All right, so let's take a look at this one. We've got big f of x is equal to 6x cubed times 7x to the fourth, and we're trying to find the first derivative. So this is an example where we can use product rule, right, because we have the product of two different functions. So what could we let our little f function be equal to this time? Good, 6x cubed, which means the g function is going to be what? 7x to the fourth. Perfect. Now, for our formula, remember, we're looking for the derivative. It's going to be f g prime plus g f prime. That means I need the derivative of the g function and the f function for this formula now. Well, what is f prime going to be equal to? (18x squared). Good. And what is g prime going to be? Good. 28x to the third. All right. Now we have all the pieces we need for our formula. Okay, so we make sure we start with the f function here. That's going to be 6x cubed times g prime, which is 28x to the third, plus, then we take our g function, 7x to the fourth, times f prime, which is 18x squared. Now it's just a matter of simplifying, right? So if we multiply 6x cubed times 28x cubed, what is that term going to give us? Good. So 168. And then we add the exponents, so that's x to the sixth, plus, now if we multiply the 7x to the fourth times 18x squared, what's that going to give us? Good. 126. Again, we add those exponents, 4 plus 2 gives us x to the sixth. Now we have like terms, so we can actually add these together. So when we do that, what are we going to get? (294) x to the sixth power. Good. So that is our first derivative now. So that's an example of our product rule. Okay, so again, anytime you've got the product of two functions, identify the f, identify the g, find the derivative of each, and then you're just going to plug into the formula f times g prime plus g times f prime, and always simplify whatever you can. Any questions on that one? Now, I want to show you on this one specifically, we could have actually simplified the original function first and then found our derivative, and you should get the same answer. Okay, so if we were to actually multiply these out, because we could, what would that give you for the original function? Right, 6 times 7 is 42. Add your exponents, that's x to the 7th. And now, sorry, if we want to find f prime of x, now we could just use our power rule, right? Multiply the 7 times the 42, drop your exponent by 1, and that's also going to give us 294x to the 6th. Okay, so that's definitely the shorter way to do this one, okay, but I definitely wanted you to see how to do it using product rule, because there will be times where, you know, one of your functions is a polynomial like 6x cubed, but the other piece is sine of x, right? Well, you can't do anything with those. You can't multiply them together, so you have to use product rule in those cases. But if you can simplify the original function first, that's probably going to be your best bet, because the derivative is probably going to be easier to find that way. Any questions on that one now? All right. Example 7. So we know that h of x is equal to x times g of x, and that g of 3 is 5 and g prime of 3 is 2. We want to find h prime of 3. Okay. So a lot of stuff given here, right? But it's kind of tricky to look at and think about, well, our h of x is in terms of g of x, right? What do you think we might want to do first here, though, based off of what we're trying to find? Okay, so split the terms up. And when you say split them up, what do you mean? Okay, good, right? So let's take the x and the g of x, and we're going to find the derivative of h of x here, but we're going to use our product rule to do that. So we're going to let f be the x, and we're going to let g be the g of x function. Right, well, remember, if we're going to use product rule here, because this is x times g of x, we're going to have f times g prime plus g times f prime, which means I need to know my derivatives for each of these now. Well, what's the derivative of x? One, right? So we know that derivative is 1. What's the derivative of g of x? Okay, so it's not 1, right? Because the derivative of an x value would be 1, because that's the slope of that line. If I just want to represent the derivative of g of x, how would you represent the derivative of g of x? G prime of x, right? That's all we can do here. Okay, since all we know is that it is a g function, right? G of x, All we can say is that it's g prime of x. Now I'm going to substitute everything into my formula. So we're looking at h prime of x. We're going to start with the f function, so that's x times g prime, which is just g prime of x, plus, then we have the g function, which is just g of x, times the f prime, which is just 1. Okay. Now we're almost there, okay, because we're trying to find h prime of what? 3, right? So all I really have to do at this point, if I'm looking for h prime of 3, what are we going to do? Plug in 3, right? So everywhere I see an x, I'm going to substitute it with a 3. So we're going to have 3 times g prime of 3 plus g of 3, and then times 1, right? We don't really need that anymore. Well, looking at the given information now, we know all of this information. So h prime of 3 equals 3 times, what is g prime of 3? 2, right? So I can just put 2 there. And what is g of 3? 5. Now we simplify. 3 times 2 plus 5 is going to give us what? 11, and that is our answer. So again, even though it looks a little tricky, just based off the information that's given, just start with the fact that you know you're looking for h prime of some value, find that derivative, right? And in this case, the only way we can do that is to think of the derivative of g of x as g prime of x. But then once you go to plugging your number, then you have all the information you need, and you can just substitute those values in there. We do have to use a product rule in this one because there's no other way to simplify that first. Okay, so we have to think of it as x and g of x separately, use product rule to find that derivative. Any questions on that one now? All right. Quotient rule. Okay, so now if we have the quotient of two functions, f of x over g of x, and as long as both are differentiable here, then we can use this formula. Okay, so we have g of x times the derivative of f of x minus f of x times the derivative of g of x, and all of that goes over g of x squared. Or again, if you want to simplify it, this is g f prime minus f g prime all over g squared. So that is our formula now for quotient rule. Okay, now the key with this one is start with g, right? Because I know with product rule, right, the formula we use starts with an f, okay, but you got to start with a g, and it's important that you do that here because you're subtracting in the numerator, so the order here does matter. Okay, so it's always g f prime minus f g prime, and then all of that goes over g squared. Yes. Okay, so these formulas are not given to you, right? So your power rule, your product rule, your quotient rule, you're going to have to know all of those. And then the same thing as we move through the unit, there's a few other rules that you're going to have to know. I don't give those to you, right? You have to memorize them. You have to know how to apply them. That's why I said, every time I do these problems, like with the limit ones, right, I always write down the limit definition as I do the problem. We'll do the same thing with product rule and quotient rule throughout the unit. That way, hopefully, the more you write it down and see it, the easier it'll be to remember it. All right, so let's take a look at this one now. So we want to find the derivative, y prime, and we have a quotient, x squared plus x minus 2 over x cubed plus 6. All right, so what's the first thing we're going to need to do this time? Okay, good. We need to identify the f and the g so that we can actually use our formula. So what are we going to let f be equal to this time? The numerator. Good. So it's x squared plus x minus 2. Okay, so f is always your numerator. G then has to be the denominator, so that's going to be x cubed plus 6. Now, what do we need to find to be able to use our formula now? Derivatives. Good. What is f prime going to give us? 2x plus 1. Good. And then our g prime is going to be what? 3x squared. Perfect. All right. So now, if we're looking for y prime, this is a quotient. So we start with g times f prime minus f times g prime all over g squared. All right, now we have all the information we need. We just have to substitute it in. Start with your g function. It's going to be x cubed plus 6 times the derivative of f, which is 2x plus 1. Then we subtract. Take the f function, x squared plus x minus 2. Multiply by the g prime, which is just 3x squared. And all of that goes over g squared. So x cubed plus 6 all squared. Any questions up to that point? All right. Now, I always just keep my denominator factor. There's no real reason to actually expand that out. Okay, but the numerator we do need to multiply out, combine any like terms that we get. Let's start with these first two binomials. If we multiply this now, we can use FOIL. So we have x cubed times 2x. That's going to give us a 2x to the fourth. Our outer terms here would be plus x cubed. Inner terms will give us a plus 12x. And then our last term, 6 and 1, plus 6. And then down here, we have to distribute the negative, but we also need to distribute this 3x squared to each term. So that's going to give us a negative 3x to the fourth. And we're going to have a negative 3x cubed. And then finally, the two negatives make a positive. 3 times 2 is 6x squared. Again, I'm just going to keep this factored, x cubed plus 6 all squared. And always check my work as I go, because I can make mistakes too, right? So just make sure if you see something that doesn't look right, please speak up. Any questions on that step? All right, so now we just need to combine like terms in our numerator. So if we do that, what are we going to get? All right, so we have a negative x to the fourth. Good. Combine your x cubed terms here. That's going to give us a negative 2x cubed. Perfect. We don't have another x squared term, so that's just plus 6x squared. There's only the one x term, so that's plus 12x. Same thing with the constant 6, nothing to combine that with, so we get a plus 6. And all of that goes over x cubed plus 6 squared. And we're done, right? So nothing else to do. There's no common factors in the numerator, so no reason to try to factor that. Leave that alone, right? And you, again, you can just keep the denominator factor. In some cases, what will happen is you'll have factors in the numerator that cancel out with a factor in the denominator, which is why it's always best to keep the denominator factored anyway. Okay, but in this case, nothing we can really do with that numerator. Leave it alone. That is our derivative. Any questions on that one now? So just so you know, quotient rule is one of your longer processes, right? We've got one other one that might sometimes get a little longer even than this one. But keep in mind that it's still shorter than that limit definition, right? Because if we had a quotient like this and we were substituting x plus h in for all of your x's and having to expand all that stuff out and then simplify, we're going to have compound fractions to deal with. Right? This is still a shortcut, even though there's more steps compared to some of the other shortcuts. Okay. All right. Now, if we have negative exponents, so in this case, they're saying n is a positive integer, and then we're making it a negative. If we take the derivative of x to the negative n, we can still apply our power rule just like we would before. So we're going to move the negative n to the front. We're going to subtract 1 from that exponent, and that's still going to give us our derivative. Okay, so whether you have positive exponents or negative exponents, we can still use our power rule. All right, so let's take a look at this one. So we've got y equals 1 over x, and that's just a comma. Okay, so 1 over x. We want to find dy dx, so we want to find the first derivative. Now, the first thing I want to do here, what's another way that we could write 1 over x? So if you have a variable in the denominator like that, another way that we could write it. Okay, almost, right? So x to a negative power, what would the negative power be? It would be negative 1, right? So I'm going to rewrite my function as just y equals x to the negative 1 power. Now we can just use our power rule to find this derivative. So if I'm looking for dy dx, what's our derivative going to be? Almost. So try not to skip steps here, right? Think about, if you go step by step here, what would it look like first? And then we'll rewrite it. So we're going to bring down the negative 1 times x to the negative 2 power, right? We bring down the exponent and we subtract 1 from our exponent on the x. Now we can rewrite this and make the exponent a positive, right? So we can move it back to the denominator. And if we do that, what's it going to look like? There we go. Negative 1 over x squared. So that x to the negative 2 goes to the denominator, becomes an x squared. Negative 1 just stays up top, though. And so we get negative 1 over x squared. And that's why I said I would, change it to a negative exponent. Think of it as a power rule. Write out the steps if you need to, because it's really easy to forget that negative that goes up in the numerator if you don't. Okay? Any questions on that one? All right, so now we're looking for d dt, again, just the first derivative of 6 over t cubed. So what's our first step going to be? You could, right? So you could do this as a quotient rule if you wanted to. Think of the numerator as f, think of the denominator as g. But in this case, we can actually think of this one just like we did the previous one. So how could I rewrite this instead? Good. So I'm just going to say this is 6t to the negative 3. Okay, so whenever you've got a simple fraction like that, where it's pretty easy just to bring the t up to the numerator and make it a negative exponent, this is going to be the shorter way rather than having to go through the quotient rule, right? But if you use quotient rule and simplify, you're going to get the same answer. Now, what would our derivative be if we take the derivative now? Good. Negative 18 t to the negative 4. And again, we're not going to leave those negative x on our variable, so move that to the denominator. Perfect. Negative 18 over t to the 4th power. That's our answer. Okay. Just to show you, I can do it pretty quick here. If we let f be the numerator, which is 6, and g be the denominator, which is t cubed, derivative of 6 is 0, and the derivative of this, it's going to give us 3t squared. And then when we plug in, we're going to start with g, so that's going to be t cubed times f prime, which is 0, minus, and then we're going to take the f, which is 6, times g prime, which is 3t squared. I'm going to put all of that over g squared, which is t cubed to the 6th. First term cancels out, becomes 0, so we get a negative 18t squared over t, sorry, this should have been t cubed squared. So that's t to the 6th. And then 2 of those t's cancel out. And so we get a negative 18 over t to the 4th. So again, quotient rule gives you the same answer, right? It's just more unnecessary steps than you really need to do there. Any questions on either one of these now? All right. All right, so general version of our power rule, if n is any real number and we have x to the n, we can actually use our power rule. Okay, so it doesn't matter what that number is, as long as it's a real number, can't do it with imaginary exponents, then we can use power rule here to find the derivative. All right, so let's take a look at this one. Okay, we're given here that f of x is x to the pi power. We want to find f prime of x. Well, pi is a real number. We can use our power rule. So what's that going to look like if we take the derivative this time? That's it. Bring down the pi, keep the x, subtract 1 from the exponent, and that's all we can do there. Since pi is an irrational number, right, don't round it or anything like that. So the only way we can write that exponent now is just pi minus 1. Any questions on that one? All right, so let's look at b. So we've got y equals 1 over the cubed root of x squared, and we want to find the derivative. So what should we do first here? Good, right? So let's rewrite this fraction. And so we know it's going to become negative because it's in the denominator. We can rewrite radicals using fractional exponents. So this just becomes x to the negative 2/3. So remember, the exponent becomes the numerator. The index of your radical becomes the denominator. Because it's in the denominator, we know it's going to be a negative exponent. Any questions about how I converted that one? Okay, now we can find the derivative. So dy dx. We can use our power rule because negative 2/3 is a real number. So what's our derivative going to look like this time? All right, so negative 2/3 x to the negative 5/3. That looks good. If you subtract 1 from negative 2/3, you're subtracting 3/3, right? So that's where the negative 5/3 comes from. You just bring down the exponent to negative 2/3. Now we don't want to leave the negative exponent. So how could we rewrite this now? Good. Okay, so the negative 2 stays up top. 3 was already in the denominator, so it's going to stay at the bottom. X comes down and becomes x to the 5/3. Now, I'm fine if you leave it just like that. If you want to convert it back into a radical, you could, right? Since the original one was in radical form. So you could write this as negative 2 over 3 times the cubed root of x to the 5th power. So this is an either or, right? So I would take either one of those answers there. And I guess technically you could take out an x cubed from that one in the denominator. So you could also simplify this to negative 2 over 3 times x cubed root of x squared if you really wanted to. So any of those three answers is perfectly fine. Any questions on that one now? All right. Now we want to find the derivative of this function, f of t equals square root of t times a plus bt. All right, so in this case, t is the variable. A and b represent real numbers. Okay, so just keep that in mind as we're going through to find the derivative. T is the only thing that's a variable. A and b are real numbers. What do you want to do first here? Product rule works, right? So we could do that. What else could we do? Just so we kind of know there are options for this one. What's another option? Okay, so we would find f and g to do the product rule, right? Okay, so that's one way we could do this one. Is there any other way we could do it, though? So it will involve power rule, but what would you have to do first with the function that's given so that you use power rule instead of product rule? Distribute, right? So there's two options here. We can either think of this as a product of square root of t and a plus bt, or if you want to distribute first, then everything actually just becomes a power rule and we can do it that way. Okay, so again, up to you, does not matter to me. Since you said power rule first or product rule first, we'll go with that. So f here is going to be the square root of t, and then we'll let g be equal to a plus bt. All right, now, how are we going to find the derivative of square root of t? Okay, good. So we need to convert it to t to the 1/2 power first, right? So square root of t, same thing as t to the 1/2. So now when we find the derivative, what's the derivative going to give us? Good. 1/2 t to the negative 1/2. So we bring down the 1/2, subtract 1 from the exponent, 1/2 minus 1 should give us a negative 1/2. And I'm going to leave that derivative as is for now, right, as we substitute it in. I think that's going to make it easier to combine like terms and things, and then we'll deal with the negative exponent at the end if we have to. All right. What about g prime? Just going to be b, right? Because the derivative of a, if a is a real number, that gives us 0. Derivative of b times t, b is the slope of that linear function now, and so b is our derivative. Any questions about how we got that? All right, so now if we're using our product rule, f prime of t, we're going to have f times g prime plus g times f prime. All right, so start with f. Again, I'm going to use t to the 1/2 here just to make things easier to combine as we go. We got t to the 1/2 times g prime, which is just b, plus, then we have our g function, a plus bt, times f prime 1/2 t to the negative 1/2. All right, so now I'm just going to kind of rearrange these terms here. So this is b times t to the 1/2 plus Now we can distribute here, and if we do that, what are we going to get? Basically taking everything in this set back here and distributing it to each of those terms there. Okay, good. 1/2 a t to the negative 1/2 is that first term, plus, and then we're going to have 1/2 b t, and it's going to become a positive 1/2 because we're adding those exponents together, right? T to the first power plus a t to the negative 1/2 power is going to give us that. Now, look for like terms. It probably would be easier to use power rule here, right? Distribute first and then use your power rule. But in this case, it doesn't matter, right? It should give us the same answer either way. If we combine like terms now, notice we've got this b times t to the 1/2 and a 1/2 b times t to the 1/2. We put those together, what do we get? Good. 3/2 b t to the 1/2, and then we have our 1/2 a t to the negative 1/2. Because again, the coefficient of the first term is just a 1, and then we're adding the 1/2 coefficient. 1 plus 1/2 is 3/2, and then we just keep the bt to the 1/2. Now, the only other thing you might want to do here, right, is get rid of that negative exponent, move it to the denominator. So I'm going to keep this as 3/2 bt to the 1/2 plus, I'm going to write my 1a in the numerator, keep the 2 in the denominator, and this becomes t to the 1/2 down here now. And if you really wanted to, right, you could put the bt to the 1/2 in the numerator with the 3 for that first term. You could also change these back into square roots if you want to. There's a few other things you could do, but if you at least get it to that point, then I'm good with that. I think the book also like factors out a t to the negative 1/2 here, and then keeps everything else in parentheses. That's fine if you really want to do that. That's useful if you ever need to set this equal to 0 or something like that, just to have the factored form. But we'll look at that more along the lines. Yeah, if we need to, we'll do it that way. But otherwise, getting it here is fine. Any questions on that one now? All right, I think I'm going to stop there because I think the next example is going to take me longer than the 2 minutes we've got left. So we'll pick up here with example 12 tomorrow and finish up these last 2 examples in this section. And we'll also get into the next section tomorrow. Like I said, we'll kind of see how far we get, and then I'll adjust the homework as needed. The 2.1 to 2.3 homework, though, is still going to be due by midnight tomorrow night. So just make sure you're working on that one. Let me know if you've got any questions. But then the 2.4 to 2.6 homework, that one might get pushed back even further, but you've at least got the weekend to get that one done for sure. Okay. Again, let me know if you got questions. Send me those questions in WebAssign. Come see me during student hours if you need to, right? That's 9 to 10 every day before class. So come see me if you need to ask me any questions there. Otherwise, have a great afternoon, and I will see you all tomorrow.